Hi everyone, welcome back to the wonderful world of annuities. In this video, we'll talk about calculating future value of annuities. Let's look at a future value of an ordinary annuity problem. Rita Grant wants to accumulate a sum of money to pay for graduate school. Rather than investing in a single amount today that will grow to a future value, she decides to invest $10,000 a year over the next 3 years in a savings account paying 10% interest compounded annually. She decides to make the first payment to the bank 1 year from today. So this is an ordinary annuity problem. The present value is 0. We don't know what the future value is. That's what we're trying to calculate. N equals 3, I equals 10, and we have 3 equal installments of $10,000 each. So we need to use Table 3, future value of an ordinary annuity. Read down the far left column till you get to 3 periods, N equals 3. Then read across till you find 10%. And at that intersection, we have a factor of 3.31. Multiply that factor times 1 installment of $10,000, and you end up with a future value of this ordinary annuity of $33,300. So $10,000 invested at 10% at the end of each of the next 3 years will grow to $33,100. Here's some math they put together for you. I cut through the math and went directly to the tables, as did they in this example. Same thing we did a few moments ago. Here's another problem. It's the same exact scenario as the last problem. Rita wants to accumulate some money to go to graduate school, and she decides to invest $10,000 a year over the next 3 years in a savings account paying 10% compounded annually. But instead of making her first deposit at the end of the first year, she decides to make the first payment immediately. And we need to know what the future value would be. How much would Rita accumulate after 3 years? Same problem, but instead of an ordinary annuity, it is an annuity due, a different table. Present value is 0. We don't know what the future value is. 3 equal installments of $10,000 each at the beginning of each compounding period. N equals 3, I equals 10%. Let's go to Table 5. Future value of an annuity due. This is Table 3. Table 4. Table 5. Future value of an annuity due. Count down to 3 periods and across to 10%, and you have a factor of 3.6410. Multiply that times 1 of your equal installments of $10,000. 10,000 times 3.641 equals $36,410. So the future value of $10,000 paid 3 times over the next 3 years at 10% interest is $36,410. And here's the solution presented on the slides. $36,410, doing it the math way, and using the future value of an annuity due table, table 5, $10,000 times 3.641 equals $36,410. Here's another concept check problem for you, but this one is a little tricky, so let's work it together. On January 1st, 2021, the Stench Fertilizer Corporation, I didn't make that up. I wish I had. They decided they needed to accumulate $8 million for plant expansion. The funds are needed on January 1st, 2026. Stench intends to make 5 equal annual deposits in a fund that will earn interest at 7% compounded annually. The first deposit is to be made on January 1st, 2021. The present value and future value facts are as below. These factors that they give you are taken from the present value and future value tables 1 through 6 at the back of your book. I just checked them. They are accurate factors for a future value of an ordinary annuity, 7% for 5 years, a future of value of an annuity due, 7% for 5 years, present value of 7% for 5 years, and present value of an ordinary annuity of $1 at 7% for 5 years. So what is the amount of the required annual deposit? Little tricky here. The correct answer is A, but let's walk through the calculation. We know the following facts. The future value is $8 million. N equals 5. I equals 7%, and we don't know what the payment amount is. We do know that we have a future value of an annuity due situation because the first deposit is going to be made on the first day of this 5-year period. So if we look at table 5 and read row 5 across for 5 years, n equals 5, table 5, n equals 5, and read it across until it intersects with 7%. We get a 6.1533 factor. Now the problem dropped off or truncated these last 2 digits, so we'll truncate those last 2 digits so we calculate the same answer as the problem. So the factor we want to use is 6.15. Let's go back to the problem. And so we're using this factor right here. Now, it's not a matter of multiplying that factor times the future value. That doesn't work. In a normal future value calculation, we take our payment times a factor to calculate the future value. Well, we don't know what the payment is, but we can turn and restate that formula as future value divided by the factor will equal the payment. So if we take $8 million and divide it by 6.15, we will calculate $1,300,813 rounded. Here's another somewhat tricky problem. Let's go through it together. I, R. Wright, plans to make quarterly deposits of $200 for 5 years into a savings account. The first deposit will be made immediately. The savings account pays interest at an annual rate of 8% compounded quarterly, how much will Wright have accumulated in the savings account at the end of the 5-year period, round to the nearest dollar? These factors that they're giving you are correct. We do need to figure out a few things. First of all, the deposit will be made immediately. So this is a future value of an annuity due problem. Future value of an annuity due is either this one or this one. Now let's think about it for a few minutes. We have an 8% interest rate, but that's an annual interest rate, and we're compounding that rate quarterly. We're gonna put the $200 in every 3 months, 4 times a year, and it's going to compound quarterly. So we can't multiply 8% times something 4 times a year, because it's an annual 8% rate. So we have to divide that 8% by 4, and we're going to be using a 2% interest rate. Then think of the number of periods. It's a 5-year period, 5-year savings account, but we're going to put the money in 4 times a year. So 4 times 5 equals 20 compounding periods. So this is the factor we want to use. And if you take 200 times 24.7833, you end up with $4,957 rounded. So the answer is C. So this is a problem where the compounding period is more frequently than annually. And that's an important concept. It's going to be used in a number of situations in an accounting situation. So you might want to back up the video and review these calculations several times before you move on. And now that you've had an opportunity to review that problem where the interest was compounded more frequently than once a year, you should be able to answer this problem then. U.B. Wong plans to make quarterly deposits of $200 for 5 years into a savings account. The deposits will be made at the end of each quarter. The savings account pays interest at an annual rate of 8%, compounded quarterly. How much will Wong have accumulated in the savings account at the end of the 5-year period, round to the nearest dollar? Why don't you do the calculations, choose your answer, and then come back and see if you were correct? Well, this problem is exactly the same as the problem presented in the previous slide, except that Wong will make deposits at the end of each quarter instead of at the beginning of each quarter. So the problem is a future value of annuity problem, not a future value of an annuity due problem. It's a future value of an annuity. So the answer should be future value of an ordinary annuity, or this one. It should use either of those factors. N equals 20, I equals 2%, times this factor. Did you choose answer D? $200 times 24.2974 equals 48.59 rounded. Well, that's all for this video. When we come back, we'll calculate present values of annuities. See you next time.